let's say we have a first order differential equation and we're trying to solve for y as a function of t. And let's say that our equation is the derivative of y is equal to some function, and let's call it f of t and y. And let's say that this function f can be factored into the product of two continuous functions of t and y, and let's call those functions m of t and p of y. And so our equation becomes the derivative of y, and we'll use the Leibniz notation here. Is equal to m of t times p of y. So this equation can be considered a separable differential equation. And the first step of solving such an equation is to separate the function of y from the function of t. And to do that here, we can divide both sides by p of y, which is the same thing as multiplying by 1 over p of y. So we can actually call that the function n of y. So when we multiply both sides by n of y, we get n of y times the derivative of y with respect to t is equal to m of t. And once you have it in this form, if we integrate both sides with respect to t, then on the left side we can use u substitution. So if we say that u is equal to y, then du is equal to the derivative of y dt. And so now our integration is in terms of u on the left side, so it will be the integral of n of u du is equal to the integral of m of t dt. And so now if we can integrate both sides, then we can back substitute, and that will give us the solution for our equation. But instead of doing all of this, we can actually take a shortcut. When we had our equation in the form n of y times the derivative of y is equal to m of t, if we pretended like we can separate the derivative in such a way that if we multiply both sides by dt and this dt cancels out, then we would get n of y dy is equal to m of t dt. And so if we just integrate it like this, then that would get us to our solution much faster. And to show how both of these methods actually lead to the same solution, we will solve this initial value problem. And we'll use both methods side by side so we can compare. Now the first step in both methods is actually the same, which is to separate all y's and the t's in the equation. And to do that in this equation, that would mean to divide both sides by y squared, which is the same thing as multiplying by y raised to the negative 2. So when we do that, we get y to the negative 2 times the derivative of y with respect to t is equal to 6t. And because this is the same step as the other method, we can move this to the other side. Now the second step in the first method is to integrate both sides with respect to t. And so if we use the u substitution, then we would say that u is equal to y, and so du would equal to the derivative of y dt. And so now on the left side of our equation, we can integrate in terms of u. So that will give us the integral of u raised to the negative 2 du is equal to the integral of 6t dt. And that would give us on the left side negative 1 over u is equal to 3t squared plus the constant of integration. And the reason why we didn't include the constant on the left side is because it got absorbed in this one. And when we back substitute for u, then we would get negative 1 over y is equal to 3t squared plus c. And this is an implicit solution for our equation. But if we were to use the other method, we would separate the derivative dy over dt. So when we do that, we get y raised to the negative 2 dy is equal to 6t dt. And then we integrate both sides like this. And when we do that, we get the same implicit solution, which is negative 1 over y is equal to 3t squared plus c. Well, there you go. Both methods result in the same solution, but the second method is much faster. So now that we have our implicit solution, we can either solve for y and get an explicit general solution, or we can plug in the value of our initial condition to solve for the unknown constant. And we can do that at this point, so let's go ahead and do that. So negative 1 over 1/25 is the same thing as negative 25 is equal to 3 times 1 squared is just 3 plus c. So when we subtract 3 from both sides, we get c is equal to negative 28. And now plugging this into the general solution gives us the particular solution that satisfies the initial condition. And that will be negative 1 over y is equal to 3t squared minus 28. And then when we solve for y, we get y of t is equal to 1 over 28 minus 3t squared. And this is the particular solution that satisfies our initial condition.